And then on Friday, we'll do a review. I'm still trying to figure out like what type of exercise I want to do because I don't think the breakout rooms are beneficial. They would be if everybody participated, but I think sometimes it's just not beneficial. So I'll come up with something else. I'm gonna share my screen so we can get back cracking on this. Handout. So I think we left off. Where did we leave off? So we're gonna do this question right here today. Just highlight it, and we're gonna finish up. The reaction wheel down here. Finish these last questions, and I think that's the whole worksheet. Let me see. Make sure we're not missing nothing. And then I put two of those questions as on your own type, on your own questions. So you need to do those before you turn this in. Where is it?
Wasn't it the electrophilic one that you have? It's like right above.
Yeah, it's right here. It's the on your own, Davidic, just putting the arrows in. And then right here, predicting the product. Now this reaction right here is the same as chromic acid. It's the same thing. All right, that's actually the chromium trioxide and sulfuric acid. That's the precursor to chromic acid. So it's the same type of reaction. It's oxidation. All right, let's go up to here. And it says in this question, that if you have a strong acid, epoxide readily cyclized intramolecularly, so it's given a clue as to what's happening. And it says propose a mechanism for the cyclization. Now, I know when we talked about the epoxide opening, one of the things we talked about were the conditions, right? We said if you open them under acidic conditions, then they open at the most substituted site, or they can open at the least substituted site. So I want to show today, we're going to talk about this. But if you notice in the product, we got a, yes.
This is like the epoxide opening, right?
Yes.
Do you mind if you can? Because I've like rewatched all the lectures and I haven't grasped the epoxide reaction.
Mm-hmm.
So do you mind like telling me like what's going on here basically with this reaction?
We're about to go through the mechanism, so let's do that first, and then if you still have questions, we can hash them out. But with epoxide, I forget. I think it's in that one of those videos. But with the epoxide, it's okay. Let me just give you. Let's just do this. All right. If we had an epoxide like that, that epoxide. Sorry about that. Both of those carbons in that epoxide are electrophilic, right here and right here. Right there, because there's a dipole going towards oxygen in each case. All right, so these are partially positive. That means you can react them with a nucleophile. So the nucleophile can either attack either side. It can attack here. Let's hold up. Let me move that over. All right, so if I attack that with a nucleophile, it can attack this side over here, the arrow. Or it can attack here. whichever side it attacks, it's going to pop the ring open. Right. So if it attacks on this side right here, then the ring is going to open like that. Right. And so what you'll be left with in that case is, I think, yeah, so that's a CH3 there. So the OH is going to be on this carbon. And then the nucleophile will be bonded to the other carbon. And by the same token, if I open on this side, then that's going to open that ring that way. So the nucleophile will be here. Whatever nucleophile I use, it'll be on that side. And then the OH will be here. Right, so it just depends on the conditions. Least substituted side is going to be under neutral conditions, and then the most substituted side it'll open, it'll attack under acidic conditions. But this particular example is kind of different because it's intramolecular. So we're going to look at that. Did that help any?
It did. But like you said, I think reps should just help. I'm just trying to grasp the concept, just see how I need to study it. But the OH, I get the part with the nucleophile attacking and opening the epoxide, but
so the hydroxyl part, this part is going to come in a quench step, right? Because when you open it, it's actually going to be O-, right?
Okay, thought so.
And then you need to add in a proton source to make it the OH. That's why most of the times when you do these types of reactions, you do the opening first and then you do a quench. Every reaction has some type of quench or workup that you do at the end. So that's why it becomes an alcohol.
Thank you. That helped.
All right. So let's go to this example. So we know it's intramolecular, meaning that it's going to cyclize using the atoms that are already in place. There's nothing external that's going to come in, right? And we actually have a choice here, and I'm going to talk about both choices, right? Because you have a choice. You can make a 5 or a 6-member ring. And so that's why I was saying that it's a little bit different in this case, even though it's done under acidic conditions. You're going to get to the 6-member ring, let's just add in H plus because that's what the sulfuric acid is there for. It's a source of H plus. All right. So with that being added, what happens is my epoxide, let me see if I can copy that.
Dr. Russell, did you just say the base was a source of the H plus?
Yeah, no, here.
No.
The sulfuric acid.
Okay, yeah, okay. I'm just making sure I was following.
Yeah, that's why my H plus is coming from. Let me wipe this out too right quick. So the H plus, the proton source is going to be sulfuric acid, and that's going to activate my epoxide. Right, so what's going to happen is I'm going to actually, this oxygen has 2 lone pairs. So I'm going to coordinate a proton to that oxygen. Let me not coordinate it. I'm actually going to bond it. So now that oxygen becomes positive. All right. Now, as far as the ring opening is concerned, right? You got, again, on your epoxide, you have 2 places that can be attacked. And if you look in the product, you can see that it's the oxygen group here that opens your epoxide. The question is, which side is it going to open from? So if let's count the carbons. So we start here, 1, 2, 3, 4, 5. If it opened there, that would actually give me a 5-member ring. So let's see what that would look like. So if it opened here at this site, and this pair of electrons went here, what we would actually get from that is a, let's see, 2, 3, 4, 5. I'm gonna put the oxygen here. All right, and so with that, once that happens, the other carbon that was in the epoxide is going to be here. So this is one of your carbons. This is the carbon that got attacked. And then that carbon is actually bonded to the second carbon, which I don't have shown, but I'm going to draw it in. So this is the other carbon in the epoxide right here. And that carbon is going to be bonded to an OH group, which is here, right? And you can see that this OH group right here is this, comes from that oxygen, right? So if it attacked, put my numbers back in. So this is going to be 5. Come on, pen. This is 5. That's 4. That's 3. That's 2. And oxygen was 1. Right. That's how I had it numbered up top. And I'm missing CH3.
Dr. Russell,
Yes.
I'm trying to see how the epoxide got from like the original way it was to the structure you drew. I know like the OH comes in there. I get that part. I just don't get how like the epoxide is shaped differently. Like what's going on there?
Well, no. The epoxide is gone, right? Because the oxygen, let me put this in here too, because it's still protonated. The oxygen came and attacked the epoxide. This is the epoxide right here. I'm trying to pick a different color. Let's see. I'll use blue. So this is the epoxide right here. And because that oxygen attacked one of the carbons in the epoxide, you see the other arrow is showing that you're breaking this bond right here.
Yes.
Yeah. So when you break that bond, the epoxide no longer exists. That's why I showed the 2 carbons down here, right? The ones highlighted in yellow.
Oh, okay.
Right, because if I were to do this, push these electrons back to the carbon that's labeled 5, I could pop that back open and go right back to my start material. Right, but so the epoxide is not there anymore because I broke it. I popped it open. All right, so that's where the cyclization part comes in. That I cyclized it. I went from a acyclic compound, which I started with up top, to a ring. That's what that means when we say cyclization.
Okay. I see, because I was confused because it wasn't the same exact structure as the top, but I see what you did there. Now
Yeah. I popped that ring open intramolecularly. So I used a pair of electrons from inside the system, pre-existing pair of electrons, to attack the epoxide. And then if I just bring in the conjugate base of sulfuric acid, right, that'll do proton transfer here. I'll write it over here. That's going to take care of that proton. All right, so the conjugate base will come in, do a proton transfer, boom, here, get rid of that proton, and then that's how you'll have your 5-member ring product. Both are possible, but I'll explain why one of them is favored over the other after we show the formation of the 6-member ring.
This is helping Dr. Russell.
Good. All right. So that's 1, 2, 3, 4, 5, like that. All right. So now I'm going to take the same image, but in this case, what we're going to do is we're going to pop the epoxide open at a different place, and you'll see the difference. Oh man, I didn't try to do that. All right. So if I take that, let's number it. So we already numbered. Going the opposite direction, we can see where we got the 5-member ring from. But let's number here. 1, 2. I need a thinner pen. Sorry. So this is 2, 3, 4, 5, 6. Right. So if I want to get that 6-member ring, that means that that I have to attack the epoxide from the other side. Are y'all following that? So I'm not going to attack it at the 5 carbon like I did over here. I'm going to attack it on the other side at carbon 6. All right. So if I add in H plus, I'm going to get the same thing. This is going to get protonated. It's got a lone pair, positive charge. And so now it's activated. So now I can actually hit the epoxide. Let's see. From the other side. So I'm gonna just draw an arrow to here. And when I do that, that's gonna break the CO bond in the epoxide. Right, it's gonna break this bond right here. And give those electrons to oxygen. Right, so that's gonna give me a 6-member ring. Like so. And we'll go in and put the other substituents in. So we know we got a CH3 group here. And then this is the carbon that got hit. This is the carbon that was bonded to it. So on that carbon, that's where you're going to have your OH group. Like that. So we go back in and renumber them. This is 1, that's 2, that's 3, 4, 5, and 6, like that. I need to put the proton here, sorry. All right.
Dr. Russell.
Mm-hmm.
On the first structure, you started 1 at OH, right? So why, when you get to the ring, the number 1 is the oxygen, and then number 2 is by the CH3?
That's why I just put that step back in. That's still atom number 1. Right? It's still it's right here. So that's still atom number 1. And it's attacking atom number 6. Can you see that? And it's still an OH until I come in with the conjugate base and take off that proton.
I think I kind of get it, because is that? Oh, okay, I get it.
So it's the same mechanism. You're just getting a difference product, a different ring size. Instead of getting a 5, you're getting a 6, which is what's up here in the product.
Okay.
So that 6-membered ring, it will be your product. We got a methyl group here and an OH. Like that. Right. So the question up top that says in presence of strong acids, epoxides readily cyclize intramolecularly proposed mechanism. So the mechanism is just first you do proton transfer right here to activate your epoxide. So let me put that in. So I think I can, yeah.
When you're done ready, can you scroll down a bit?
Mm-hmm. So the proton transfer is to activate your epoxide. And then after that, it's just intramolecular epoxide opening. So that's this step right here. Then you do another proton transfer. Right? And then that gets you to your product. So the question now is, okay, so this is what I want to get at, kind of. Which side of that epoxide do you think is more substituted? If you look at this starting material. So right here, right where we started. When you look at each carbon in that epoxide, I'm gonna scroll back out too, by the way. I'll zoom out.
The epoxide is just the region where, yeah, where you just highlighted basically.
Which carbon in there is more substituted?
The one that's on the top, basically.
Is it the top one?
Yes. Okay, so if we're doing this under acidic conditions, you would expect that carbon will be more susceptible to attack, because that's basically the idea, right? If you do it under acidic conditions, you can attack the more substituted carbon and pop the ring open. If you do it under neutral conditions, you attack the least substituted carbon and pop the ring open. So the question now is, why does this product predominate? We've seen the mechanism. We see that you can get both products. And in all honesty, you probably get a mixture of both. But why do you think the 6-member product predominates over the 5? I've been thinking about this question all night, to be honest.
Isn't it like you just said, like the 6-member ring will be more substituted, right? So it'd be more susceptible to get attacked, which is what you want to do with the epoxide, right?
Well, if you look at where we get the 6-member product from, the OH is actually attacking the least substituted carbon. Am I right? Based on what we just did up top, you see the 2 pink highlighted carbons right there. We just said that the one on top.
Is it because the least substituted one gives you the 6-member ring, whereas the other one gives you the 5-member ring?
So it comes down to, yeah, it's in that vein. It comes down to ring size and ring stability. Now, and we didn't talk about this a lot in part 1. I hate that we missed that section dealing with the chairs and different cyclic systems. But the 6-member ring is slightly more stable than a 5-member ring, slightly. And so more than likely, that's going to lead to that product predominating, even though you're doing it under acidic conditions, right? So it's kind of counterintuitive, but when you look at the ring size, the 6-member ring is going to give you a little bit more stability than a 5. Normally the trend is the smaller the ring, the more strained it is and the higher in energy it is. And as you go up from like a 3-member ring to a 4-member ring to a 5 to a 6, the energy goes down, which is good. So the 6-member ring is the more energetically favorable product in this case. And I know we didn't have a lot of time, we didn't do a lot of discussion about 6-member rings and chairs and bolts and all that stuff. And I really hate that we didn't get a chance to talk about it. But if you want to know more about it, I have a whole video dealing with that and dealing with the different steric interactions that happen in 6-member rings and stuff like that. But I know we didn't get a chance to do it last semester in part 1.
I have one more quick question.
Yeah, go ahead.
Can you kind of explain to me the difference between like the neutral conditions and acidic conditions one more time, please?
Yeah, so neutral conditions would be if I just took this ring and let's just say I didn't have sulfuric acid, I just heated it up, like increased the temperature. Or I took the epoxide and I treated it with some nucleophile, like let's just keep staying the same vein, like LAH, with no other acidic, nothing acidic in the solvent, like we did it in LAH, and we did it in like THF as the solvent, right? That would be considered neutral, as opposed to being acidic, where you're doing it in the presence of something protic, like acid or alcohol or something like that.
Thank you so much.
Mm-hmm.
Dr. Russell, is that why the OH attacks the most substituted?
In this case, yeah, you're gonna get both products, but the product here that's shown is gonna be your major product. And the reason is because you get a larger ring size, a 6-member ring as opposed to a 5-member ring.
So the OH is gonna always attack the more substituted carbon then?
No. In this case, it attacks the least substituted carbon because the product is a more stable product. But which carbon gets attacked is going to be dependent on the conditions. If it's done in the presence of acid, then it's going to attack the most stable, the more substituted side. If it's done and without the presence of acid, it's going to attack the least substituted side.
Okay.
But because this is intramolecular, it's a little bit different.
Okay.
So basically, when it's intramolecular, we should be looking to see what the product is before we choose.
Yep.
Okay.
And thinking about the size of that ring that you're making in the product, because this is a cyclization, right? And so if this epoxide opening happens intramolecularly, it's going to cyclize into some other type of ring system, be it a 5 or 6 or 7 or however many carbons.
So just to finish what Kayla was saying, when you're like dealing with the intramolecular reaction, you're gonna look at the product to see see where the OH attacks the carbon, right?
Yes.
Okay.
Let me fix this up over here. Let me move on to another question. I think we only got a couple more questions to do. All right. I'll fix that up before I post it. Let's go to this set of reactions, these multiple choice reactions. So that top reaction is some type of reaction that we've already covered. So is the second one. So is the third one. What's the answer to the for the top reaction? What would you choose?
The top far right.
Top right. This one.
Yes, sir.
Okay. What type of reaction is that?
Esterification.
Good. It's an esterification. Good. What about for the second one?
That is the acetal. I don't know.
Close enough. Close enough. Acetal.
I was trying to pronounce it right, so
Yeah.
I knew what it was.
Yeah. Which product is it?
It's gonna be D. So the bottom right.
Okay. This one, I agree. All right, what about the third one? What type of reaction is that? And what's the product?
That's gonna be, it's gonna give you a carboxylic acid, I think.
Is this like the Gabriel Synthesis one?
It is.
Hmm.
Yeah, so you'll get the NH2.
No, I'm wrong. I spelled it like a name. Well, like a, no mind. I spelled it wrong. Right. So the Gabriel synthesis is a way to make amines. Right, from alkyl halides. So it's going to be this product right here. All right. And so the quick and dirty way to think about it, if you don't know the mechanism, find the leaving group and replace it with an NH2. It's that simple, right? Find the leaving group, replace it with an NH2. That's exactly what you have right here. Right, but what gives it away is a phthalimate. Phthalimate, strong base, and an alkyl halide. If you got those three things, then you know it's going to be a Gabriel synthesis. All right, let's go up to here. And let's finish these last two reactions. And then I think that's the last thing other than the on your own questions. And
The most grocery pickups I ever did.
all right.
They want you to do like 10 in 4 hours. Like, ma'am, I can't go that fast. Especially when they do grocery lists.
You need to mute your microphone.
They my shifts are usually 8 hours. Each grocery round will take you about 45 minutes start to finish. It will take you about 45 minutes to start to finish. And when I tell you what makes a
That's a whole conversation there. I'm glad that's more important than this. All right. So we're going to finish these last two reactions on this wheel, and then we're actually going to stop. I'll take some questions, and then we'll get ready for Friday. I'm gonna find another set of questions, and then it's just gonna be like an open season type of thing. It won't be something that you have to turn in though. All right, what about this reaction right here?
So that's gonna be, I think it's gonna be a Wittig reaction.
I agree with you.
And that turns like an aldehyde or ketone into an alkene, I believe.
Yeah, you're right.
Yeah.
So what's the final product? All of this, let me put the other stuff in. So all this stays, right? The ring stays. That doesn't change. These carbons don't change. What changes is that functional group, because it won't be a ketone anymore. So what would be at the end of that double bond to make it an alkene?
CCH3CH.
Yeah. Because you're subtracting it, like the HBr from that.
So it's going to be, you said CH, Hold up.
Yeah, street.
Yeah, I said C, yeah.
Like that. Is that what you're saying?
Yes.
Okay.
Yeah, I agree.
All right. So that's the Vedic. And you again, it's a conversion of a carbonyl into an alkene. It can be a aldehyde, it can be a ketone, it can be an ester under certain conditions. But it's going to turn that into an alkene. This is a very powerful reaction and widely used as well, because it's with under certain conditions, you can control the stereochemistry. You can control it and make the alkene cis or trans or E or Z. So it's a very powerful reaction. All right, the last reaction is right here.
And that's the Gabriel.
Or is it shift space?
It's a
I
shift
said,
base.
I don't know. Okay.
Gabriel synthesis will have phthalate, right? You got to have phthalate in order to do that. So this is a shift base synthesis. All right. What is a shift base? Well, imine. That's the proper name for that functional group. It's an imine. So you got a primary amine, right? And you're gonna use that to convert the carbonyl into an imine. What's the imine? What's the functional group? The imine functional group look like? So all this, none of this changes.
Would it be the like N plus the alkyl group?
That's the imine. For those of you who are taking part 2 lab, did y'all make these this semester? We normally do.
No.
Oh, yeah, we normally incorporate that into that lab. We make the chalcone, and then we make the imine, and we make the isoxazoline. But I'm not sure with all this COVID crap. I don't know how much y'all were actually able to do. But anyway, again, the reagents for that are primary amine and aldehyde or ketone. There's another type of product you can get from that if you use a secondary amine, and that's what's called an enamine, but we're not going to talk about that. I think it's in the video, but I don't have any problems dealing with that, so I'm going to leave that out. All right, so these problems right here, you need to do on your own before you turn this in. This problem and its label. And you need to finish that Vedic problem up top. That's labeled too.
So the electrophilic addition one, you didn't want us to do on our own? Because I thought you had said that, but I just want to make sure.
Yeah, we've done this, right? We've done these reactions already when we did aromatics. So yeah, you should be able to do these reactions with no problem.
All right.
Yep. All right, any questions about anything? All right, so Friday I need to figure out the structure of that class, like how we're gonna do that. And then the exam, again, for those of you who are listening, and because you didn't get it or hear it, that don't mean I didn't say it, because I know there's other things going on, people at work, people driving, whatever. But the exam is gonna be on respondents. So you need to get all of that stuff ready to go. All your browser, your webcam, all of that stuff, you need to have it ready to go to take that last exam, because it's going to be on a lockdown browser. And the final as well, it's going to be on lockdown browser, because we're not going to be able to be in person. And I don't really like ProctorU because it's just too much hassle trying to set up those exams on ProctorU. So that final will be a respondents exam, and this last test, which is not the final, is going to be respondents. Final is on the 21st. We'll have a couple of review sessions before the final.
It's on the 20th.
Yeah, it's on the 20th on the sheet.
20th. I'm thinking about the it's a week after the senior final, which is on the 13th, which is tomorrow. So if you are a graduating senior and you're not listening, that's on you. The final is tomorrow between 1 and 3. I'll probably extend it into the evening for those of you who work, but it's got to be taken tomorrow. It's got to be taken in one sitting. Not tomorrow, the 13th. My bad. The senior final is on the 13th, and it's got to be taken in one sitting. You'll have 2.5 hours to take it, and it's going to be on respondents. So, but the test tomorrow is open for everybody, whether you graduating or not. You still got to take it.
Friday?
Huh?
Wait, I'm kind of confused now.
Okay.
I thought tomorrow,
tomorrow is the
that's
13th.
Friday.
Hold up. Tomorrow is exam 6. That's for everybody.
It's on Thursday?
Friday.
Tomorrow's Thursday.
I'm tripping. Friday.
Yeah, tomorrow's the 13th. So graduating seniors is tomorrow.
Tomorrow is the 13th. Graduating senior final. Friday is exam 6. So if you're a graduating senior, then you'll have taken up to exam 5. You'll take your final tomorrow, which is Thursday, the 13th. On Friday, that's exam 6 for the class. Everybody else who's left in the class. And then on the 20th, that's when our final is for the class. So graduating seniors take finals on the 13th, which is tomorrow. Friday, exam 6 for the rest of the class. And then the 20th, which is a Thursday, that's when we'll take our final for this class.
And Dr. Russell,
Yes.
can I chat with you a minute after class, possibly?
Love to chat, don't you? You just love to chat.
I just gotta talk to you about something.
All right.
All right.
I have a question.
Okay, go ahead.
So for the final, is it gonna look like the exams that we've already taken, or is it gonna look different?
What do you mean by that?
Like, is it gonna be like the same type of questions, or should we like study from our book? Because I was just gonna go back and look at my old exams to study for the final.
It's not gonna be the same questions. So if you it's gonna be the same topics. Right?
Well, yeah, I mean, like it's the same like type of questions, not the same exact questions.
Well, yeah, it's gonna be multiple choice questions, matching questions, no fill in the blank, because Blackboard does a horrible job with filling the blank questions as far as matching up the answers. I don't do that. But yeah, it'll be the same type of questions, the same format.
Like the same topics and everything.
But it'll be the same. It's going to be the same topics, but the questions are not going to be identical to what you've seen. But it'll be the same format.
Right. Okay.
So looking over the old exams, yes, that's one way to study. But you also need to be looking at your notes. You also need to be looking back at. You can use the syllabus. You can look at some of the problems in the book that are listed in the syllabus. Like, I wouldn't just go back and look over the old exams, because that's going to give you a false sense of security.
Yeah, I was just thinking like, because I know some of the sections in the book we kind of like skipped over, or we just like
or condensed them.
Yeah, but
Yeah.
Okay. Thank you.
All right. Any other questions? Did I stop recording? I think I'm still recording. People hearing all our business.